All right, for 4.6, we're going to talk about natural log functions which have and use the natural base e. So if you remember at the end of class, you watched a video on the difference between simple and compound interest. And this equation right here represents compound interest. Compound interest is interest that keeps paying on the principal plus the interest that's already earned. So if you remember, P stands for our principal, N stands for the number of times that the interest is compounded. T stands for how long this investment is being compounded, how long it's there for. And then we already talked about N. R stands for the interest rate that's earned. Okay. So for a natural base, E represents an irrational number, a number that goes on forever. It's defined as 1 plus 1 over n to the power of n. So imagine our time would just be 1. This represents 1 year. But now we're going to take the number of times interest is compounded and just slowly start increasing it. So if we plugged in a 1, that means interest is compounded annually. If we plugged in a 2, that would be semi-annually. 3 would be 3 times a year. 4 would be quarterly. And then if we keep going, monthly, and we can go every day. And you're going to see this on the warm-up in class, that as we slowly increase the number of times that interest is compounded, meaning paid throughout the year, we're going to slowly approach this number, which represents E. It's for an interest rate that is continuously compounded. We're going to write that formula down here below in a sec. We call it a natural exponential base because it rises naturally in real life situations. Okay, so our function, because it's growing, this would be exponential growth. Our exponential function would be f of x equals e to the power of x, where e represents this 2.7. It's something that's compounded continuously. Our two equations for something that's compounded, we already talked about interest that's compounded annually, semi-annually, daily, weekly. Something that's compounded continuously would look like this. The amount equals our principal with a base E to the power of our interest rate times time. Everything else, semi-annually, quarterly, annually, would use our formula up above. Okay, and then I want you to take a look at the difference down below. Quarterly, monthly, and then so on and so forth. Would be A, our amount, equals our principal times 1 plus our rate divided by the number of times it's compounded to the power of n times t. Okay, and I want us to see the difference in the same the same principal that's plugged in, the same amount, but one that's compounded continuously and one that's compounded monthly with the same interest rate. You'll see a slight difference between the two of them. Okay, so why don't you take a second, let the video pause, plug these into both equations and see what you notice about an investment that's compounded continuously versus an investment that's compounded monthly. All right, go ahead. For continuously, our $2,500 with a base E, compounded continuously means repeatedly in infinite number of times, times 10 to the power of 0.5. So over 10 years with a 5% interest rate, you would have gotten $4,121.80. Okay, for something that's compounded monthly, you should expect this amount to be a little bit less. Monthly would only be 12 times a year, when compounded continuously is an unlimited amount of times throughout the year. Okay, so this would be 2,500 times 1 plus our rate, 0.05, divided by 12 times a year, and then 12 times our 10 years, and you would have gotten an amount of $4,117.52. So clearly, compounded continuously is going to make that investment increase at a greater rate. Okay, I want to go ahead and graph our parent function with the natural base e. It looks like this. Let's make our table. Remember, we're always going to let e equal 2.7. We're just going to estimate e equals 2.7. We might need e squared in here, 7.4. We also might need 1 divided by e in here if we plug in some negative values, which would be 0.37. Okay, so we have those values here. We can go ahead and plug them in, -1, 0, 1, and 2. -1 gets us 1 over e, 0 is 1, 1 just gets us e, and 2 gets us e squared. And we have all those values up above, right? 0.37, 2.7, 7.4. And we'll practice these a lot where you become pretty familiar with those and you almost have them memorized. All right? Let's go ahead and graph these here. -1, 0.37, 0, 1, 1, 2.7, and 2, 7.4. All right. So it looks just like an exponential growth function, which is what it should look like. Domain is all real numbers. Range is everything above your y-axis. Range is y is greater than 0. But what I'd like to do now is take the inverse of this function, which is going to be a natural log, and graph that inverse and see what it looks like. So exponential functions with a base e, the inverse is a natural log, or we abbreviate natural log with ln. I'm not entirely sure why it's not NL, but it's ln for natural log, and that is your inverse. All right. Let's solve for the inverse over here. Let's take that same equation. Yeah, we'll do it right here. Y equals e to the power of x. And then we'll go ahead and switch x and y and solve for our y. So we have x equals e to the power of y. We've talked about solving for your exponent last unit. However, now if you want to solve and we have a base e, you just write the natural log of e. Just like logs have a common base 10, natural logs have a common base e, and we get the natural log of e to eliminate, and we have f -1 of x equals the natural log of x. Your table, well, we've graphed log functions before. Remember, you always want to, and we know our values right here. We could just take all of these and flip them, but I still want to just practice plugging these in because you're going to have a natural log that you're graphing down here in just a sec. But remember, you always want to plug in 1, and you always want to plug in the base. So 1, and the base is e. Our next power of e would just be e squared, and then 1 over e. All right. We know what these values are. We graph them up here. The natural log of 1 over e, if the base is e, would just have to be -1, gets that base to flip. The natural log of 1, always 0. The log or natural log of 1 is always 0. That's a property that we'll list again at the end of our notes here. This would just be 1, and then to get e squared, the natural log of e is just 1, and the natural log of e squared is just 2. Okay, so let's go graph those here. Remember, 1 over e is 0.37, so 0.37, negative 1, 1, 0, 2.71, and 1, 2, 3, 4, 5, 6, 7.42. This looks just like a log function because it's pretty darn similar. It's just a log function with a base e is a natural log. Domain is everything greater than your vertical asymptote. Range is all real numbers. And again, you might notice that these are reflecting over the line. Y equals x because they are inverses of each other. Okay. All right. Let's go graph one more function together. Let's do 3, and then you can graph 1 and 2 on your own. The way I would graph all of these is see if you have your shifts left to right and move your axes. You do have a shift here. This is up 4. Okay, so we would take our x-axis, shift it up 1, 2, 3, 4. Put our dotted line here. Remember, a base e, it's an exponential function, so that is your asymptote. And then we'll just plug in some values, and when we're done, don't forget to multiply all of the y's by negative 1. This is a reflection over the x-axis. So we would plug in negative 1, 0, 1, and 2. Negative 1 gets us 1 over e. 0 gets us 1. 1 gets us e, and 2 gets you e squared. Now just remember, these all become the opposite. So this is negative 0.37. This is negative 1, negative 2.7, and negative 7.4 because of that negative in front. Makes them all become the opposite. So we'll go graph negative 1, negative 0.37, 0, negative 1, 1, negative 2.7, and negative 2, 7.4. All right. Whoops, let's try a little bit better there. Okay, we have our function. It's going down because the base, because it's reflected over the x-axis. And then that 4 shifted our horizontal asymptote up 4. Domain, all real numbers because it's a base e, it's exponential. And range would be everything less than positive 4. Okay. Try 1 and 2 on your own. Those both have translations. So 1 and 2, they're both shifted left, right, up, or down. Don't forget to move your axes. And then go ahead and graph. Okay, for 1, that's a shift left 1 and up 2. And then you just have your parent function base. So you were just taking this table of values with negative 1, 0, 1, and 2 and plugging those in to get 1 over e, 1, e, and e squared. Don't forget you have all those values up here if you need to copy them down. 0, 3.7, or negative 1, 0.37, 0, 1, 1, and 2.7, and 2, and 7.4. We have a graph that looks like this. All right. How about for our natural log function? There's only one shift here, and we're just making a table for the natural log of x. Let's get that lined up. Okay, there's a shift left 3, and remember this is a log function or a natural log. They're both graphed pretty similar. They have vertical asymptotes, so that's going to be your asymptote. You always want to plug in the base and 1, so 1 and e, and then e squared and 1 over e. To get 1 over e, this would need to be negative 1. The natural log of 1 is always 0, and then 1 and 2. We're going to go graph those from this new origin. 0.37, negative 1, 1, 0, 2.7, and 1, and 7.4, and 2. sorry, 4, 5, 6, 7, 0.4, and 2. There we go. Domain, x is everything greater than your vertical asymptote, which is at -3, not 4, sorry, and range, all real numbers. Okay, exponential functions with a base e and natural log functions, both being graphed, just like exponential functions, growth or decay, and log functions. Therefore, the properties are identical to your log properties. Natural log properties are the same as your log properties. So if you remember, the log of 1 always equals 0, right? B to what power gets you 0? 1. The log of b with the base b always equals 1. So let's write these same properties over here for natural logs. The natural log of 1 then, as you saw above, is also 0. And then the natural log of e, because there's a base e, would equal 1. Your common log just states if you have the log of x, it's the log of x with a base b. We just don't write our 10 there. Sorry, it's a log of x with a base 10. So then for a natural log, if we just have the natural log of x, this is the natural log of x with a base e. We just don't write it. Power property, same thing. If we have the log of x to the power of m, we can rewrite this as m times log of x. So if we have the natural log of x to the power of m, we can write that as m times the natural log of x. Power property, just move the exponent in front. Product property, taking the log of something with the same base and adding it to another log expression with the same base means we can just multiply x times y with a base b. So for natural log, same thing. The natural log of x plus the natural log of y would just equal the natural log of x times y. Quotient property, when you're subtracting two log expressions with the same base, this is a good review for us, minus the log of y with the base b. We can just write this as a ratio, x over y with the base b, and you have one log expression. The same is true for natural logs. The natural log of x minus the natural log of y equals the natural log of x over y. Inverse properties, log of b with the base b to the power of x, those can just eliminate and you're left with x. Or if we had b to the power of log of x base b, those can just eliminate and you're left with x as well. So for natural logs, that would look like this. The natural log of e to the power of x just equals x, and e to the power of the natural log of x just equals x. These are inverses of each other, base e and natural logs. Change of base, log of x with a base b can be rewritten as the log of x divided by the log of b. Same is true for natural logs. The natural log of x can be rewritten as the natural log of x divided by the natural log of e. And last one are one-to-one properties. If we have the log of x with the base b equaling the log of y with the base b, well, then x and y have to equal each other. X has to equal y in order for those expressions to be or for that equation to be the same. So if we have the natural log of x equaling the natural log of y, then x would have to equal y. Okay, a lot of properties. You've seen these before. We're just using them with natural logs now. So let's practice a few of these. Starting with, I'm just going to jump around and pick about half of these to do together, and then you'll do the other half on your own. Let's start with 2. E to the power of 2 times the natural log of x. We want to use the inverse property here, but first, let's use our product property, or power property, and write this as e to the power of the natural log of x squared. And now you can use your inverse, and you're just left with x squared. Let's try 4. 4, you're subtracting two natural log expressions, so you should use the quotient property. The natural log of 5 over x equals 2. Okay, remember we need to get rid of that natural log expression, which means we need to exponentiate. And if the base is e, then we need to exponentiate both sides by a base e. And we're left with 5 over x equals e squared. We'll just leave it as e squared for now. Multiply both sides by x. 5 equals e squared times x. And then we can just divide our e squared over. And we're left with 5 over e squared. If the problem says leave in terms of e, we can just leave it like this. If we need to simplify, just on your calculator, you have an option for e, or on Desmos that I can show you another time. All right, let's try number 8 and then see if you can do the other 4 on your own. Okay, let's try 8, or other 5, sorry. Again, let's do 6 and 8. 6, you're adding, so we can combine these as a product. 8x with the base e equals 1. You don't need to write your base e if you don't want to. I'm just reminding us that we need to exponentiate by e. And we're left with 8x equals e. Divide both sides by 8, and we have e over 8. Okay, last one I want to try together would be 8. Subtracting means we are dividing. So we have the natural log of, and I think actually I want this to be us. I want us to be adding here. I'm just going to quickly change this problem to addition. Okay, because we're adding, because we are adding here, we are multiplying these two natural log expressions, so this would be the natural log of x squared minus 5x. Don't forget to distribute. And then we have equaling 5. You again want to exponentiate with the base e to both sides. Get e natural log x squared minus 5x equals e to the 5th. Okay. We would add our 5 over. E to the 5th is just, well, we can use our calculator. But if we're just leaving in terms of e, which we're going to do right now, that's fine. So we'll leave it just like this. And then we'll square both sides. And we get x equals plus or minus the square root of e to the 5th plus 5. Okay. If you needed to use a calculator, you would use a calculator. But if it just says leave in terms of e, we're just going to leave in terms of e here, and that's okay. Just leave it just like this. Okay. I'd like you guys to try 1, 3, 5, and 7. 4 problems on your own, and we'll check your solutions when you're done. Go ahead. All right, for number 1, this was just your inverse property. The natural log of e, these are inverses of each other, and you're just left with 3.2. For number 3, again, using the inverse property, the natural log of e just eliminates. So you just have 2x plus x, which is 3x. For 5, also inverse property, but when you use the inverse property here, you're left with x cubed equals 27. So you were taking the cubed root of both sides, left with x equals 3. And then finally for 7, we're adding two log expressions, so we should be multiplying. Don't forget to distribute the 3 to the x and 6. Exponentiate both sides by a base e. We have 3x minus 18 equals e cubed. Again, we're just going to leave that as e cubed for now. Add your 18 to the other side. Divide by our 3. And you have x equals e cubed plus 18 divided by 3. Just leave it like that. Most of the time, the directions will say just leave in terms of e, just like in geometry when the direction said leave in terms of pi. Same thing. E is an irrational number, so we're just going to leave it in terms of e. Okay, great work. You have some simplifying and solving natural log equations on your homework, and some graphing, exponential functions with a base e, and natural log functions, all which we will go over in class.